So if you've been following all these examples, consider pausing this and solving this, or at least attempting to solve this yourself first, and then go ahead and compare your answers. But again, another example. We have a box. Oops. We're going to be pushing it up an incline. So I'm just drawing a rough sketch so that we can draw our free body diagram based off of this sketch. We know this incline is angled at 35 degrees from the horizontal. We want to know how hard we have to push to keep the box moving at a steady speed up the incline. So I'm going to go ahead and assume we're pushing parallel to the incline, since there's no information suggesting other words. We're told the coefficient of kinetic friction. So we've already gotten this box moving and we want it to keep moving at a steady speed. The velocity is going to be constant. So if we continue pushing up the incline, meaning straight direction, steady speed, the acceleration will be 0. So our free body diagram, I'm going to go ahead and come to the left to draw that. The dot represents the box. The box, of course, is experiencing a force of gravity, mg downwards, towards the center of the earth. It's experiencing our push. I'm going to just call this F sub P for force of push. You can call it whatever you want. We just have to represent the force. The block is on the incline, and so there is a normal force perpendicular to the incline. And then there is friction. The problem gives us a coefficient of kinetic friction. The force of kinetic friction always points opposite the motion. So this force of kinetic friction is going to point down the incline. As a general rule, it is most helpful to make the x-axis along the incline and the y-axis perpendicular to the incline. I'm going to go ahead and call up the incline positive. You can call down the incline positive if you want. We just have to be careful in terms of the signs as we are writing out our force equations. The y-axis will be perpendicular to the incline. By doing this, the force of gravity is the one that's going to have x and y components. Whenever we rotate the coordinate system, the incline angle, in this case, the 35 degrees, is always between our new rotated y-axis and the force of gravity. So this y component will be mg cosine theta, because we're adjacent to that side. This x component will be mg sine theta, because we're opposite the angle. And again, those x and y components have to meet at a right angle. And so our triangle is also rotated with this coordinate system. All right, Newton's second law. Acceleration of an object is determined by the net force over the mass, or net force is equal to mass times acceleration. In this particular problem, we have a situation again where we have no acceleration. There's no acceleration in the y direction because our y direction being perpendicular to the incline, if there was an acceleration, that block would have to be moving perpendicular to the incline, speeding up or slowing down. In the x direction, there's no acceleration because we're pushing it up the incline, so straight line at a steady speed. So we know the net force has to be 0 in both the x direction and the y direction. So we can balance out the forces again. In the x direction, we have the pushing force pointing up the incline. We have friction pointing down the incline, so I have to subtract that to account for its direction. This component of gravity points down the incline as well, so I have to subtract off the mg sine theta. All of this together has to equal 0, which, of course, I meant to just balance in the first place. That pushing force up the incline is counteracting the friction force and the component of gravity pointing down the incline. So this first one is just writing out net force and setting it equal to 0. Because the acceleration is 0, we could have just jumped to this balanced situation. I'm getting in my habits of net force equals 0. I often write it out that way. In the y direction, so our y direction are the forces perpendicular to the incline. So we have the normal force pointing up and to the left, and then the component of gravity down and to the right. The normal force is counteracting this y component of gravity. All right, let's make some substitutions. So for example, we know the force of kinetic friction will be the coefficient of friction times the normal force. If I put in coefficient of friction, the y equation tells me the normal force needs to be mg cosine theta. So that whole term is my force of kinetic friction. And then we still have the mg sine theta term. Mass we need. So coming back to the problem, they have given us mass. That's good. We know the angle. We know mu. We know g. So now it's just a matter of plugging in. This force of push needs to equal mu mg cosine 35 plus mg sine 35. So to keep this box moving, I'm getting 111 newtons. I only have 2 sig figs, so approximately 110 newtons is what is needed to keep this box moving up the incline. So again, draw the free body diagram, write out symbolically the equations. So the equation F equals ma in terms of the forces, but in symbols, not numbers yet. And again, another reason for doing that is we could easily give a problem like this and you're told the force of push and that the box is moving at a steady rate up the incline, and you could be asked for the mass of the box or the angle of the incline. So it's really easy to just interchange what information is given versus asked for. So if you are writing these symbolically, it's not as overwhelming to try to figure out how to approach the problem, right? If we had been given the force of push, but not the mass, so it had been given mu and theta and the force of push. So instead of giving mass, giving the force of push, we could easily now solve for mass out of this. So writing equations out symbolically help in terms of being able to isolate whatever it is you're solving for.